Okay, we should get started. It's 3:07. Okay. I usually like to wait a couple minutes, but it's time now. All right, guys, let's quiet down. Okay. All right, so welcome back. Hope you had a good weekend. All right. So here we are in week 3, and the topic for this week is basically data types in Pirate. Okay. In the book, in chapter 11, they call them structured. They call it structured data and conditional data. And so we'll get to kind of what that means. Okay. And I don't know. Actually, we might have to push binary trees back, because today I'm going to spend some more time looking. We're going to practice more with list programming. Okay. Because the assignment is due this Saturday, PA1, and it's mostly programming with lists, getting some practice with that. Okay? So that's where we are. I suppose I can click on PA1 here. Should work, yeah. So there's a little bit about knots and then some list exercises. Just download the file and work with it and submit on Blackboard by the due date. I think that's about all. And yeah, the reading for this week is chapter 11. It's not very long. Okay, and it talks about these things called structured data and conditional data. And probably on Friday, I will go into more detail on providing some extra context and insight into structured and conditional data. Okay, we should be able to do this reading. It's not too bad. Okay. Okay. So I think there's been some confusion a little bit about, well, it's kind of a weird thing about the data types, because we haven't, we're just now getting to kind of studying data types. This is like the data type mechanism that we're using in Pirate. And so there are these things called constructors that are kind of confusing. So let me bring up, is there a NAT file? Here it is. So we looked at this before. We've got our NAT data type. This is kind of the running example that I've been using, the type for natural numbers. So of course the name of the type is NAT, and it has what are called 2 constructors. I mean, these are called the constructors of the type. So every one of these types is going to have at least one constructor, right? Or it could have many constructors. So here we have the 0 constructor and the S constructor that I was calling the successor. Okay? And so what this means is that, why are they called constructors? Because these are the ways to construct values of type NAT. They're the only ways. Okay? So if you want to construct a NAT, you could do that with the 0 constructor, and it stands on its own. You don't have to provide it with any arguments. So you can always just use 0. That'll construct a NAT. Or the other option is to use the successor constructor, passing it a NAT as an argument, and that will construct a NAT. Okay, and so you're using it almost like a function, but it doesn't compute anything. You just sort of embed a NAT inside of a successor constructor. Okay, so that's how you can construct a NAT. And then, correspondingly, when you do case analysis on a NAT, all you have to do is consider those 2 cases. So sort of what you're saying with cases n is you're saying, how was n constructed? There's only 2 possibilities. Either it was with the 0 constructor, so that's the 0 case, or it was constructed using that successor constructor with some other NAT inside. Okay? So those are the only 2 possibilities. And this is a way of just kind of, peeking at the value to see how it was constructed. And you can bind a name to the NAT inside of the successor constructor so that you can refer to it inside that case. Okay? So one thing I could show you is that I probably should have done before is it's common to define a function called pred on these natural numbers. Okay, so the idea of pred is that it's kind of the opposite of successor. It's the predecessor. So it sort of looks like -1, right? So take a natural number and sort of subtract it by 1, okay? So we'll do this as we always do with cases on the argument, okay? Okay, but then you kind of run into a funny case already. What do you do when you hit 0? You know, what's the predecessor of 0? Well, you know, 0 doesn't have a predecessor, so you can't really define this function perfectly. We'll just have to choose 0. We'll just say, okay, basically this function is not defined on 0, but so you could throw an error instead if you wanted. I think, you know, pred of 0. I think it's raise is how you raise an error. So maybe it's better to do that. Okay, but then you have the successor case, and then what would you do here? Does anyone know? Right. Because when you match this case, then it binds this name to the natural number that was inside the successor. And so, you know, if you've got s of nn, that's like saying nn plus 1, right? So if you want to subtract 1, nn is what you want, okay? So that's the pred function. Okay, I guess, you know, I think it helps to illustrate what's going on here. Right, okay. And I could also, I don't know, maybe I've gone a little too fast in the past. So one thing we can do, just to kind of slow it down, is we could look at what happens when you call this nat plus function with some concrete arguments. So let's just kind of step through how Pirate evaluates calls to this function. All right? Whoops. So let's say that we want to call nat plus with like 0 and the successor of 0. Okay? So, you know, this is like saying 0 plus 1. So what happens? When Pirate sees this, what does it do? Well, it begins by just taking these arguments and substituting them for the formal parameters in the body of the function. So the first thing it does is to just take the body of the function and substitute in 0 for n, so that n becomes 0, and s of 0 for m, which occurs here and here. So this will become s of 0, and this will become s of 0. Okay, so we did the substitution for the parameters in the body. And so now we continue evaluating this. Okay, then how does Pirate evaluate a cases expression? Well, the first thing it does is evaluate because this could in general be any expression. So the first thing to do is to evaluate what's here to a value. Okay, but here it's already a value, so there's nothing to do in that step. So we'll just skip it. Okay, and then once it's got a value here, it can match it against the case patterns. All right, and so, you know, here of course it'll match the 0 case, and so then it just evaluates to whatever expression is on the right hand side of that case. So this one's pretty easy. It evaluates to that right here. Okay, and then this is now a value, and so we're done. Right, we're done evaluating this expression. So there's one example. But now we could look at a little, slightly more interesting one. Okay. Let's say we want to evaluate this. S of 0 plus S of 0. That's like 1 plus 1. All right. So we proceed just like before. The very first thing that we do is take the body of the function and substitute these values for the arguments. Okay, so I'll copy this. And here was n, which is now s of 0. And then m was in these two spots, and it's still s of 0, so it's the same. Okay, so now we're there. And then, let's see, I forgot this. Okay. Okay, then we evaluate the cases expression. Of course, it has to bring this down to a value, but it already is 1. So we can skip that. And now, this time, when it matches the value against the cases, it'll match this pattern. And it will bind the name we gave here to the thing that was inside. Okay? So what this whole thing steps to, we could say, is going to be this with 0 substituted for nn. Okay? So I copy this. Okay? There's going to be 0 there, because that's what was inside the successor. All right? And then what will this do? Well, it has to evaluate the argument to the successor, because this is like a function call, sort of. And what does Pirate do for a function call? Well, it first evaluates all the arguments to values, and then passes them in. Okay, but then it's a constructor. It's like a special kind of function where, well, there's nothing to do. Once you have the values there, then they're just kind of stuck, and we don't go through the whole thing that we did here. But okay, but we already know what this evaluates to from before. That's what we did. And it evaluated at s of 0. So this whole thing is going to be s of 0. Sorry, it's not at the bottom, but there you go. Okay, so now we've kind of stepped through a couple concrete examples. I could have continued here explicitly carrying out the derivation for this call, but we already did that before. All right. So I guess sometimes it can be helpful to kind of step through what happens when you call one of these recursive functions, sort of how it recursively operates. But one of the things that I'm trying to emphasize, though, is that a lot of the time you don't have to do that, right? Is there a question?
Yeah, so s of 0 is 1, right?
Yeah.
So the answer for s of 0 plus s of 0 is s of 0, is that right?
It's s of s of 0. So that's the successor of the successor of 0.
I can see that.
Oh, yeah, sorry, it's kind of cut off. I don't know. I suppose I could drag it over.
So nn, could that be any variable name? Or
Yeah, we could put anything there. We get to choose what's there. Well, where was the function? It's up here. Right, we can choose what to put there. But I wouldn't use n or m, because those are already being used. And in fact, Pirate, it might not allow you to reuse one of those names. Not sure. Yes, yeah, this thing, so we said s of 0 is 1. Well, that's, maybe I should emphasize that by itself, this nat type is just data, right? The natural numbers by themselves don't really mean anything, right? That we're just saying it's just this collection of elements where, well, one of them is 0, another one is the successor of 0, another one is the successor of the successor of 0, and so on. There are infinitely many of these possibilities. And then it's the way that we use those values that gives them their meaning as natural numbers, right? So it's like when I define this nat plus function, I'm defining it in a way that corresponds to addition when you're interpreting these as natural numbers. So, right, so when I say, s of 0 is 1, I mean, that's how we're interpreting it, okay? But, really, by itself, s of 0 is just s of 0. It doesn't really mean anything. Okay. Okay, so as I was saying though, a lot of the time you don't need to think operationally about recursive functions like this. That you don't really need to kind of imagine in your head what happens when you run it. It can get very confusing, right? I think that's sort of why recursion gets a bad rap a lot of the time, because when you try to think about it the wrong way, it's very confusing. But so I like to emphasize this kind of inductive reasoning where like when we're looking at this function definition and you see the recursive call, just kind of treat that sort of like a black box. Like, who cares what happens when you call it? Just assume that it's correct, right? Just assume that you can do the recursive call there and it'll do the correct thing. And so then in this case, you're like, okay, assuming that I can add n and m together, however that happens, how do I turn that into the right result? We'll just take its successor, and that's it. Okay? So this kind of thinking, this kind of inductive thinking, can make your life a lot easier when doing recursive programming. Okay. So I suppose we can move on now to the list stuff. Okay. Let me find it. Here it is. Okay. So let's remind ourselves where we were. We defined a list length function here. Okay. Where it takes a list of any element type. That's what this A was for. It just says that, well, we don't care what the type of the elements is. It could be anything. And then we'll return a number. And the idea is that it'll be the length of the list. And this function was pretty straightforward. We do case analysis on the list. And there are two cases for the list data type. It's either the empty list or a link constructor. And of course, the length of the empty list is 0. And in the link case, we recursively compute the length of R, the sublist, and then add 1. Okay? So, I suppose we could, or if you want to help convince yourself that this is right, you could, step through what I did previously with some concrete list, maybe like, this one at the bottom, and just run through the steps to see how the function evaluates on one of the lists. Okay. All right. Okay, and then we did this list sum function. Okay, and it's kind of similar, except it actually cares about the type of the element because we're computing the sum of all the numbers in a list of numbers. Okay, so we'll take a list of number and produce a number, and it proceeds by case analysis on the list. In the empty case, the sum of the empty list is 0. And then in the link case, we can recursively compute the sum of the rest of the list, and then just include the element in the sum. Okay, so that one's pretty straightforward. Okay. Now the other one we looked at was list member. To check if a given element is in a list. So here we don't care what the type is, but give me an element of type A and a list of elements of type A, and I'll tell you if that element is in the list or not. Okay, and of course it proceeds by case analysis on the list. In the empty case, well, nothing's in the empty list, so of course it must be false. And then in the link case, we want to be true if f is equal to x or x appears somewhere else in the rest of the list. So I wrote this Boolean expression here. It's a compound Boolean expression using OR. Okay? You say, okay, it'll be true if f is equal to x or x is somewhere in R. That's a nice, concise way of writing it. And so this function will just search through the list looking for x. All right. Don't want to spend too much time reviewing, but it's okay. Okay, so this next one we looked at, list string lengths. Okay, list str lengths to compute the length of a list of strings. All right, so the idea here for this function, it takes a list of string and produces a list of number. So this is the first one that we've seen that has a list in the return type. All the other ones, they would take a list and use it to produce a number or a Boolean or something, but this time we're producing another list. Okay? And so, right, the input is a list of strings and the output is the list of the lengths of those strings. So it should have the same length. I mean, this list should have the same length as the input list. Okay? Right, so again, case analysis on the input list. What do you do in the empty case? Well, the corresponding list for the empty list is going to be the empty list. And then in the link case, yeah, this is where f is a string and r is a list of string, the rest of the strings. And we just needed to, do the recursive call. What do we do here? So you can do the recursive call on R. Okay, so that'll give us the list of lengths for all the strings in R. Okay, and then we just needed to tack on the length of f in the front. Okay, so I guess this is kind of a, since we're taking a list and producing a list as the output, you see a link here and then a link here. And you're doing something to f and just doing a recursive call on the rest. Okay, so that's a pretty common pattern. Okay. Now this is the last one that we looked at before. List pos nums. Okay. So this function should remove all non-positive numbers from a list. So now it takes a list of number and produces a list of number. And we do case analysis on the list. Empty goes to empty. With the link case, this is where we need to check if the element there is positive or not. Okay? And if it is, if this is true, then we will include it. So we'll do the recursive call and include f. Okay? So this will recursively remove non-positive numbers from the rest. And then f was positive, so we keep it. Okay, but if f was not positive, then we'll only do the recursive call and leave f out. Okay, so those are the ones that we looked at last time. So now let's move on to something new. And these are in the book. At least most of these are in the book. So if you're doing the reading, you should be familiar already. So let's take a look at this one. List alternating. So it should remove every other element from the input list, keeping the first. Oops. Okay. So this one's a little bit trickier maybe. Okay. And if we look at the test case, okay, this is just a way of building up the list from 0 to 10, probably not including 10. So this will be 0 through 9, right? And we say, well, if we call list alternating on the list containing 0 through 9, then it should keep every other element, including the first. So the even numbers. Okay, so how do we go about implementing this? Well, we'll do what we always do to begin with, case analysis on the input list. Okay, it's pretty obvious. Okay, and we have the empty case. And what we do in the empty case, it's again pretty obvious. It'll be the empty list in the output. Okay. But then, in the link case, now what will we do? If you recall, so maybe you could do the recursive call, right? list alternating on R, and then try to use that somehow. But it's not really clear. If you think about, well, list alternating R, well, since list alternating keeps the first, then this is going to keep the first element of R. But really, the first element of R is the one that you want to get rid of, right? We want to keep F, because that's our first element. And then the next one, we want to not keep. So this probably isn't going to work, okay? So probably, perhaps the most straightforward way to do this is to do another case analysis on R, okay? We want to get to that first element of R. So we'll do this, okay? I'll do another cases on R. All right. Now it could be empty. Okay. So what do? This is the situation where L, our whole list, is link F R, where R is empty. So it's just the list containing a single element. And so what do? Well, we'll just return that list like this. And that will be the overall result. And it satisfies what we want. Okay. So this function, if you give it a list with one element, then it'll just give you that list back. Okay. But then we have the link case, and it's always hard choosing names. I'll just say F2 and R2. And then what do? So now when you do this, nested cases, we're peeking in not just at the first element of the list, but we've actually got the first two elements. And then the rest after that. All right? So now, perhaps you can imagine that what we want to do is recursively call list alternating on R2, and then leave out this element when we reconstruct the list. So let's try that. List alternating in R2. Okay. And then include F, because we want to include F in the result. Okay, we're leaving out F2. That was the second element. Okay, so let's see. Let's see if this works. I suppose it should be 16 passing.
Can we use underscore for F2 instead?
Can you repeat that?
Can we use underscore for F2?
Yeah, you can do that. All right, so this pass. So what he asked is, can you use an underscore? I think it means here, right? And yeah, we can, because since we're not using F2, we're just kind of forgetting about it. It's good to do this. This is like saying, I don't care what this is, right? So I don't even want to have a name for it because I'm not going to use it. So you're making your intent clear that you're not using that. So this should work, yeah. Okay, so the book gives some more explanation of this. I'll leave it at that for now. Okay. So yeah, it's a little trickier in this case, right? Because you're doing double cases. All right. Still got time. All right. What's our next one? Okay. This one's interesting. List append. So this is obviously a fundamental operation on lists. If you've got two lists, you might want to append them together so that it'll be all the elements from L1 followed by the elements from L2. Okay? So of course you want to have this operation available. But how do we implement it? Okay? Let's right away we're faced with a decision. Okay? Normally the way that we start is very obvious because there's just one thing for us to do case analysis on, right? But here there's two. So which one do you do case analysis on?
Pick the first one.
That's a good idea. That's a good idea. We can try that. Okay, so let's do cases on L1. All right. So we have the empty case. So what do we do in the empty case?
Another case. You check if L2 is empty or not.
Well, you could do that. You could do that. But you don't have to. So if you think, what's, I could write this equationally like we did with the natural numbers. What do you think?
Just make a link that will eventually return to the case that we have to know it. Makes this result will be encapsulated in another link.
Well, that might work too, but there's something easier. Yeah?
You just put the second list.
Yeah, you can do that. So if you think about it, what's the empty list appended with anything?
The other one.
Yeah, it's just the other list. It sort of is like 0 plus n. Well, it's just n, right? So that's what we can do. That's the easiest. You could come up with other ways, but this is the most straightforward. Okay, so that's the empty case. It's nice and easy. But then the link case. Okay, now what? Well,
You can link, do link of FR. Wait. Yeah, you can just do a nested link basically with the other list as the rest. So link of FR, comma, L2.
oh, I don't think that'll do quite what you expect, because then you'll end up with a list of lists when you do that. If you say link of link and then the rest of the list, then you're putting a list. That link constructor is making a list. And so if you do that, you're ending up producing a list of A. So it's not quite right.
Yeah, so you would link F to the list append of graphs outfit or R outfit. Does that make sense?
I think that's right.
So it would be link F, link append R outfit.
Yeah, I think that's right. So let's think about this. So if I've taught you anything, it should be that when you've got the rest of the list, you've got this sub term of the input, you can do the recursive call on it, right? So let's think about that. Whoops. So if we recursively call list append with R in place of L1 and L2. So what's that going to do? Well, if you assume that it's correct, then it's going to append, it's going to give you R followed by L2. And so then, if you take that, how can we turn this into the final result that we want? Well, we could just link F to the front. Okay, so it may be a little tricky to see it first, but you can do this. So fundamentally, this is kind of the same thing that we've been doing all along. It's just a little, now there are two arguments, and so that makes it a little trickier, I suppose. Maybe a little surprising. Okay. So let me see if this works. Of course, I don't have a test case for it. I could add one. What do we do? List 1, 2, and list 5. Oops. 1, 2, 5. See if that passes. And so, if you want to think about what happens, when this runs, okay, say we use these as the inputs. What will it do? It'll say, okay, well, L1 is this, so let's do the recursive call on R, which is going to be the list containing 2 in this. So then you'll be recursively calling with the list containing 2 and the list containing 5. Okay, and it'll hit the link case again, and then you'll be adding the empty list with 5, which will give you 5. And then on your way back out, you're appending 2, and then appending 1. Hopefully that's not confusing, but okay, it passed. 17. But I think a lot of the time it's better to not even get bogged down with thinking about operational details of how it's executing. Sometimes you care about that if you're worried about performance. Okay, and perhaps it's helpful when you're learning, but in practice when you're programming like this, you generally don't have to do that. Okay. All right. So yeah, that one is interesting, I think. Okay, and then this is kind of, you can sort of ignore this. This just computes the nth triangular number. It's just there for like one of these test cases, okay? Okay, still got a bit of time. So let's take a look at another function. This one should compute the list of running sums from the input list. So that means, empty list goes to empty list, singleton list goes to singleton list, unchanged. Then here, what you're doing is you're kind of adding as you go along. If you start from the left, you've got 1, and then you should have 1 plus 2. So that's why that's 3. And then here, if you keep going, you've got 1, and then 1 plus 2, and then 1 plus 2 plus 3, right? And so on, okay? So we want to write a function that will pass these tests, okay? And then there's this big one to be really sure that we've got it right. So let's try it, okay? This time our job is easy. There's only one input list. So we'll do cases on it. Okay, and we already see that empty goes to empty, right? Okay. Now for the link case. How do we do? So this is also kind of tricky. Okay. So we can try our normal thing. Let's say, well, we can do the recursive call on R and assume that that computes the running sum of the rest of the list. Then there's kind of an issue with that. Because when it's computing the running sum of the rest of the list, it's not taking that into account. And when you think about how this should be going, these elements over here should include the values to the left somehow, right? That they have to be kind of aware of what's the sum up to this point. And so when you do it this way, it's kind of tricky. It is possible. One of the students that I met with had a solution that works in this way, where it's possible to take this and then to kind of write another function that runs through all the elements here and adds up to them. And then you link f on the front. So it's possible to do it this way, but there's a better way. Okay? There's a better way, and it uses a new technique that we haven't seen yet. Okay? Called we'll be using an accumulator. All right? So also a helper function. So I'm going to write a helper function, or an auxiliary function. So let's forget this. It's kind of a failed attempt. All right? And the first thing I'm going to do, and this might seem weird to you, is I'm going to define a new function. Okay? I'm going to do it inside of here because it's only intended to be used in here. Okay? And I'll just call it list running sum aux. It's an auxiliary function for us to use. And it also takes a list. I'll use a different name. I don't want to reuse L. I'll call it LL, whatever. Okay, it takes a list and number, but it's going to take an additional argument for the accumulator. Okay, I'll call it ACK for accumulator. and it'll be a number. Okay, so it'll become clear eventually what we're doing. And the result is list of number. Okay? And so this is where we're going to do all the recursion. Okay? All the recursion, all the legwork will be done by this auxiliary function. Okay? And it'll be a lot easier for us to do it this way because we've got this extra thing to help us, the accumulator. Okay? So let's do the empty case. Well, that one was easy, right? Empty goes to empty. Move this up. Okay. Okay, and now, in the link case, now it's more interesting. Okay. So again, we can do the recursive call on the auxiliary function, okay, and pass it an accumulator argument. So the idea here is this is where we're kind of propagating the necessary information through the recursion as you do it. So we want to, basically we just want to add f to the accumulator when we do the recursive call. Okay, so let's see what this looks like. List running sum aux, do the recursive call on R, that's the sublist, and then we're going to take the accumulator so far, the accumulated sum so far, and add f to it. X plus f. Okay? So this is kind of propagating that as this recurses down the list, it's adding, it's accumulating the sum as it goes. Okay? Yeah, but we're not quite done here because we need to remember f. Okay? So we'll go ahead and link f. I think it's not quite right yet to only link f. Okay. This isn't quite right. Yeah?
You need to link the accumulator.
Right.
That's what that's the running total, right?
Yeah.
You want to add up to.
Yep, that's right. So I would say act plus f. Okay? Because remember, the elements of the output list are supposed to be, the running total. Or maybe, is it just act?
I think it's just act. Yeah.
Just act?
I don't think it's act. Well,
Let's,
because
okay.
If you did the first one, you wouldn't want to.
I think you forgot the cases.
Oh, I forgot cases. Okay. And this is still going to not compile yet. Well, I don't know if you're right about that. Let's see. Because, well, we're not done yet with the definition. Okay? Because so far, all we've done is define a new function inside of here. Okay? And the idea is that the way that we'll implement the whole function, the overall function, is to just call the auxiliary function, list running sum aux, with the input list, which was L, and an initial value for the accumulator, which I'll make 0. Okay? See if that type checks. Okay, it's compiling. So now let's think what happens here. Well, if you pass it the empty list, then it'll just immediately hit the empty case, and okay. But then what about here? What'll it do? Well, see, if you only put ACK here, you would get 0.
I was thinking you would pass in the prop of the list, like L dot
Oh.
instead.
Let's
and then
You could
I'm
do
not
that.
Sure if that works, but because it might be but I thought that was what I was thinking.
I see. Okay. So you could probably do that, but you'd have to do an extra cases here to make sure that the list isn't empty. Because if you tried to do that on an empty list,
That makes sense.
it would be bad. So you could probably do that, but it's a little, I don't know, maybe it's a matter of taste, but I think it's probably cleaner this way. And yeah, we're passing more cases, so I think this works. Okay. So this is our first look at this technique of using an accumulator And you might think it's weird, but this is a rather common pattern in functional programming, where you've got your kind of public-facing interface for your function. That, you know, this whole thing just takes a list and produces a list. But internally, you know, it's helpful to have some extra arguments to generalize the function a little bit, because it makes it more powerful. You can do this. Okay, so we'll just define that inside and use it to produce the result. Okay, so this is not the only time that we'll see this kind of thing. Okay. Got a few minutes. Okay. Now let's take a look at one more. Okay. So maybe this will be our last one that we look at. But this should compute the average of a list of numbers. Okay? Pretty straightforward. Are there any ideas for how to do it?
First, we need a list link to the auxiliary function.
Okay, and we do have that, right? List length?
Yeah.
So we have list length.
And then we have the list sum, so we just divide them.
Sure. Okay. Yeah, so this is kind of a trick question, I suppose, because this one, we don't have to do any recursion. So we've already defined functions that we can use. So, you know, how do you compute the average of a list? Well, of a list of numbers, you add them all up and divide by the length. Okay, so let's say list sum, L, divided by list length, sorry, L. Okay. Okay. How many did we have passing before? Okay. Okay. Yeah, it works. All right. So I think that's all we'll look at today, although there's still a couple more that I kind of wanted to look at, but, oh, this concat. Maybe you should do this one as an exercise. And then we'll visit these later when we start talking about higher order functions. But this one should be pretty easy to do. There's no comment there, but it takes a list of strings and just concatenates them all together to produce one big string. Okay? So, you know, here's an example of what it should do. So you should be able to do that.
Isn't that one just basically the sum one?
It's, yeah, pretty much. Yeah. So it should be easy for you to do. Okay? And, you know, I'll start talking about structured and conditional data on Friday. But now we could have a quiz. So don't go anywhere.
Are you going to post this code online?
Yeah. I'll do it this evening. Okay? Oops. Let me... Okay, let's see. No quiz. All right, see you Friday.